All right. Next video, let's talk a bit about gravity and things falling on Earth. Acceleration near the Earth's surface. If I start getting further away from the Earth's surface, um, things will start to change. But here on Earth, these are the rules that we're going to follow. Everything on Earth falls at the same rate, regardless of. And when I look at these three things, I got a big rock, I got a small rock, and I got a feather. So it doesn't matter about their mass, as long as if there's no what's going to affect this feather that probably won't have the same impact on the small rock or the big rock would be air resistance. As long as I don't have air resistance, everything falls at the same rate. These guys will all head down at the exact same rate. Boom, boom, boom. They would all hit at the exact same time. All hit at the same time. Because gravity is pulling them all down at the same acceleration. Down here, switch colors. Now, they all hit at the same time because their acceleration is constant. So therefore, A must be the same or constant for all of them. And here on Earth, so therefore, here on Earth, it turns out experiment and math both independently tell us that the acceleration here on Earth is 9.8. Why? Meters per second squared, and that is always down. Now, down is sometimes hard to translate into a question, so we'll often say, when we actually comes time to use them in a formula, we say that it's equal to minus 9.8 meters per second squared, because down is usually given a negative value. This is for this is in math questions. This is Moody's walking by laughing at me. Fine. I'm a big guy. I can take it. I can take it when I'm being mocked by bullies.
I'm not fazed.
You're not fazed.
It's all lies.
So let's take a look at an example of a guy standing on a bit of a cliff, and he takes a ball, he throws it up, and it comes straight down. So I'm interested in what, when we talk about this being negative, what are some of the signs I might put on things. Over here, when the ball is going up, since up is positive, we would say that the velocity over here would be positive for this part of the trip. But here the ball is going down, even here, not just when it's below the man, but even here when the ball is heading down over at this part, we would say that the velocity is negative because it's headed down. There seems to be a couple of different distances here. I have the distance down here, this distance. Any distance down here would have a negative number, whereas any distance up here would be positive. And one other thing, and it doesn't matter, it's at all points in this trip, here A is negative. Because it doesn't matter, even when the ball is going up, it's slowing down, and so therefore the acceleration is always going to be down. And so it's just sometimes we have to keep track of what the signs are so our answers make sense. Now, just one last thing, which comes up time and time again in questions where I'm dealing with things flying through the air. If the velocity is starts off and it's big and it's positive and it starts to get slower and slower and slower, and the velocity is positive, and then suddenly it's negative right at the top when it's at its highest point. If the velocity is positive here and negative here, to get from positive to negative, we have to go through 0. And at the top of anything's path, its velocity in the y is 0. And that's often used in questions, and it's one of those things like when a question says, is let go from rest. That means that its initial velocity was 0. Just as when you're doing these questions, you need to read into the question and realize that the initial velocity is 0. Here, in a lot of these questions, you need to read into the question and realize at the top, the velocity will be 0. And that's often handy when I'm working out questions like this. And that's all I have to say about acceleration near the Earth's surface. Thank you.